All right, everyone, we'll get started. So welcome to the fifth lecture of the Deep Reinforcement Learning series. Today's lecture is on Advantage Actor-Critic. So before we get into this week's content, let's recap what we covered last week. So last week we went through deep deterministic policy gradients. And the way we did this was we took DQN, which we covered in the third week, and we discussed the ways in which it is similar and different to DDPG. So we compared DQN to DDPG across multiple domains. We talked about the value network architecture. So DQN takes in states, outputs a value for each action in that state. DDPG takes in state action pairs and computes a value for that state action pair. We talked about exploration. DQN uses epsilon greedy policy, whereas DDPG adds random noise to a policy network. We talked about value regression targets, where the value regression target for DQN comes from the Boltzmann optimality equation, whereas the value regression target for DDPG comes from the Boltzmann recursion for a deterministic policy. We talked about target network parameter updates, where DQN is performing synchronization of its target networks, whereas DDPG performs polyic averaging instead. And we also covered how DDPG trains its policy. For DDPG, the policy, which is deterministic, is trained by doing gradient ascent on the average action value. Great, so this week we're going to cover a number of algorithms. We're going to start with behavioral cloning, and we're going to work our way from behavioral cloning to Advantage Actor-Critic. So we'll start with behavioral cloning. We'll move from behavioral cloning to reinforce. Then we'll go from reinforce, we'll take a brief detour and discuss the policy gradient theorem, which gives us the theoretical basis of the reinforce algorithm. Then we'll discuss reinforce with baseline, and finally move to Advantage Actor-Critic. So yeah, we're going to move through these algorithms, and each one is going to be a development on the previous. Okay, so before we get stuck into the first algorithm, which is behavioral cloning, I'm just going to give a momentary commentary on the sort of motivation of the lecture. So DQN and DDPG, there are specific papers that you can go to, and these are the papers for those algorithms. So they have a sort of canonical version that corresponds to these papers, and you can mess around with little bits, but there is sort of a ground truth as to what the canonical DQN and DDPG algorithms look like. This is not really quite so true for Advantage Actor-Critic. Advantage Actor-Critic generally describes a family of methods, and any method that lives within this family is an Advantage Actor-Critic method. And so we're sort of going to focus more on the kind of general principle of what makes something an Advantage Actor-Critic method rather than any particular one. So this is going to be a bit more conceptual than the previous lectures, because we're more focusing on how do you do each of the individual parts of an Advantage Actor-Critic method that gets you that gets you any method within this family. So we're focusing less on the exact details of how you implement this, and more on what are the ingredients that make something an Advantage Actor-Critic method, and what are the general rules for how you do those different parts of the algorithm. Okay, so the first algorithm we're going to cover is behavioral cloning. All right, so this is more of a warm-up than one in the Advantage Actor-Critic family. So suppose you have a data set of good behavior. So I sit a bunch of grandmasters down, and I get them to play chess for me, and I compile a data set of what were the different board states and what was the move that the grandmaster made in that board state. Or I get someone who's very, very good at Pong or Space Invaders or something, and I sit them down, I get them to play Atari, and I have a data set of what was the screen like, or what were the few consecutive frames they saw, and what was the move they made. And so I gather this data set of good behavior, and I want to use this to train a network to do a good job, right? To train a network to complete this task. So the data set that I have consists of trajectories. So I have a data set of trajectories, which were sequences through the state space and what actions were taken at each state and what reward was seen. So this data set of trajectories, and I want to use these demonstrations to train a stochastic policy that will also do well in the environment, right? So I'm going to use this data set of expert level play to train my policy. So this is a stochastic policy, which I'm denoting by a pi here, that gives a probability of each possible action available given each state. So in each state, it spits out a distribution over actions. And it's parameterized by this set of parameters here, theta. Okay, so behavioral cloning is an algorithm for solving this problem of, if I have a data set of good play, how can I recover a policy that will also perform well in the environment? And the answer is really simple. I just fit my policy to that play that I have, that play in my data set. So the simple idea is just fit my policy to the data. And this makes the problem just a supervised learning problem of I have states that are my sort of inputs, and I have actions which are my outputs, and I just want to do supervised learning on this data set to fit this probability of action given state. And more specifically, you're going to do potentially mini-batch gradient ascent, or more generally just some gradient ascent method on the following objective. So you're averaging over the data set of different trajectories that you have, and then for each trajectory and each time point along that trajectory, you're going to maximize the log probability of the action that was taken given the state that you were in, right? So very simple. You're trying to maximize the probability of each of the actions that were taken given that you were in each state. So if we just think about how this works, if I'm doing gradient ascent on this objective, right, then I'm going to increase the log probability of actions that were actually taken in my data set, right? So that's the aim, that I want to increase the log probability of actions that are in my data set of good play. All right, before we move on, does anyone have any questions about behavioral cloning? Great, so really simple idea. Yeah, we update the policy parameters by doing gradient ascent on this objective. So this is the average log probability of the actions that are taken. And then we just loop this. So we do a step of gradient ascent, and we just keep looping steps of gradient ascent until we converge, or until we decide to do early stopping. So we have some sort of stopping criteria. Maybe we have a validation set that we use to choose to do early stopping. Maybe we wait until convergence, so we don't but then we risk overfitting. But we're just going to do gradient ascent on this objective until we're sort of done, until we reach some stopping criteria. Okay, so good things about behavioral cloning. It only requires that I have a data set of good behavior. It doesn't require that I actually know anything about the rewards that were received. So I can do this without any reference to any of the rewards that were received on the trajectories. So I don't require any information about the rewards in the environment. I just require this data set of good behavior. But the bad thing about it is it does require access to expert level trajectories. So I can't expect to do well in this if I just have mediocre behavior in the environment, because if I just have a mediocre behavior, then the actions here won't be particularly good. And so when I try to do this, I will fit to these mediocre actions and I get a mediocre policy, right? So behavioral cloning basically has this trade-off where I can get a good policy if I have access to expert level trajectories, but I don't require reward information. So the question now is, what if I have okay trajectories, so trajectories that aren't great, but I do have reward information? Is there a way that I can sort of switch around these requirements where I can use just normal trajectories, or more specifically, what we're going to be using is trajectories from the current policy. So I have my current policy. I'm going to use that policy to generate trajectories. These will usually just be okay. And I'm going to see if, instead of using the fact that the trajectories are expert level, so instead of using the fact that I already know they're good, I can use reward information instead. So I want to switch around these requirements. Okay, and this is going to bring us to the reinforce algorithm. So how do we go from the behavioral cloning algorithm, which we've already covered, to the reinforce algorithm? So suppose we have a data set of trajectories, but now, instead of being sampled from expert level play, so instead of getting a grandmaster chess player to sit down and play chess, we just generate trajectories according to the current policy that we have. So we have a current policy network, and we sample actions for that current policy network to roll out a trajectory, right? And we aggregate a number of these trajectories into a data set. So is there a way where, because I have reward information for these trajectories, I can use those trajectories despite the fact that they're only from my current policy, they're not from an expert level play? Right? So some of these actions will be better than others. And the key idea of reinforce is that I want to fit to the good actions and fit away from the bad actions. So I have each one of my the actions that's performed along my trajectory. And for each one of those actions I perform along my trajectory, if it was a good action, I want to fit to it. If it's a bad action, I want to unfit to it. And so I need a way of measuring the quality of the actions that we take along the trajectory. I need a way of saying which are the good actions and which are the bad actions. Which actions should I fit to and which should I unfit to? So one way to measure the quality of an action is just the return that was achieved following it. So the idea being that a good action should have a high return and a bad action should have a low return. All right? This is a very sort of bird-brained way of doing it. It's like not very complicated. It's sort of the first thing you would think of, right? Or maybe the second. The first thing might be, what was the immediate reward? But then you remember that you're doing reinforcement learning, and so you should care about the entire future. So you go, okay, not immediate reward then, let's use the return instead. So as our first pass, the sort of most naive way of doing it, second most naive way of doing it, we're going to measure the quality of an action as the return that was achieved following that action. All right? And then what we're going to do is we're going to weight each action by that return, by this quality measure. So we have a quality measure, which in our case is the discounted return. We're going to weight each term of this objective by that quality measure, and then we're going to try to maximize this objective. All right? Any questions at this point? Great. Okay. So let's cover the reinforce algorithm. I have an interaction step and a policy update step. And as usual, I'm going to loop these, right? So as usual, there's going to be a big arrow that loops background. So I'm going to alternate interaction steps and policy update steps. And an interaction step, I'm going to use my current policy to sample a data set of trajectories. So I'm going to, maybe I fix the number of trajectories I want to generate. So I say I'm going to go to my environment and I'm going to use my current policy to interact with the environment for 10 trajectories, say. And then I get all these 10 trajectories and I aggregate them together into a data set of those 10 trajectories. All right? So this is my first step, my interaction step. I'm just doing many rollouts and aggregating those rollouts into a data set. Then I have the policy update step. So the first part of the policy update step is that for each trajectory and each state action pair along that trajectory, I'm going to compute its discounted return, right? And this is just the formula we saw way back in the first lecture, and I think also the second lecture we covered this, but this is just that I look at all future rewards obtained after that state action pair, and then I sum those rewards and I discount by one discount factor for each time step in the future I go, right? So this is just my discounted return, right? Sum of all future rewards discounted by how many time steps away they are. So for each state action pair, I'm going to compute this discounted return. And then I'm going to use that discounted return as a weight for that state action pair in this objective. Right? So I'm going to perform one update of the policy parameters by doing ascent on this objective. So I'm doing a single gradient step on this objective. And then, as usual, I'm going to go all the way back round and I'm going to loop this. So I do one gradient update step, and then I go back to my environment, sample a new data set of trajectories, compute the returns, compute my objective, do one gradient update step, go background, right? And this is the reinforce algorithm. Great. Any questions? Awesome. Okay. So let's generate some intuition for why this works. So this is the objective that we have. And remember, it's just the same as the behavioral cloning objective, except now my state action pairs are weighted by the return. So the higher the return is, the more positive this return is, the more that you can increase this objective by fitting to that action in that state, right? So if an action yields an abnormally high return, this weight will be very high, and you will want to increase that action in that state. Conversely, the more negative it is, the more you can increase by unfitting to the action in that state. All right. So in other words, these weights, these returns act as weights, where the larger the weight is, the more you can increase this objective by fitting, and the more negative it is, the more you can increase by unfitting, right? So the weights encourage us to fit or unfit to the various actions. Yeah.
So if you want to unfit to an action, what happens for the gradients for the rest of the action? Is there any particular preference for another action, or are they kind of equally up-regulated?
Yeah, so the question was, if you unfit to an action, what happens to the probabilities to other actions? What you expect is that the network should generalize. So if there's two states that are very close to one another, and I know that in this state I want to unfit from this action, and in this state I want to fit to a different action, then probably when I try and unfit to this action, I'm going to allocate mass to the action that's preferred in the other state, right? So you'll probably, when reallocating mass, if you're unfitting from an action, you'll probably reallocate that mass to actions that that were good in other states that are similar to the state you're in. So you expect your neural network to generalize like this. Does that make sense?
Yeah. And a similar question, but just like, because we just had to talk about unlearning in neural networks, do you have a more effective way of forgetting the action in that state by, for example, moving towards the more uniform policy, or moving towards some other high-ending policy, as opposed to doing a direct reversal of gradient, which doesn't always work?
Yeah, so the question was, could you, instead of weighting the sort of term in the objective and then doing a sort of movement away from that, could you instead sort of fit to a uniform policy? And the answer is like, yeah, you could definitely do other things, but we're going to see in a moment why this particular thing to do has some justification, why it's sort of it's motivated by something rather than just being like a thing we made up.
And also, I guess in this case, there is a spectrum of returns. It's not like a binary. You want to forget this, you want to go towards this. So
yeah,
define some boundary on what is it.
Yeah. So you're right. So these returns are not just binary, like do I fit, do I unfit? They are continuous variables, and the more positive they are, the more I want to fit, and the more negative they are, the more I want to unfit. So the key idea, the key intuition for reinforce is that the returns act as weights that indicate how strongly you want to fit to each action. Just another sort of note, if I imagine I go to a state, and in my data set, that state appears 10 times, and there are 10 actions off that state, and I try every single one. So for my data set, I have that state appearing 10 times, and every different action in that state appears. Let's just think about what will happen. Imagine all of the returns are positive. So all the returns are positive. So intuitively, that means I want to fit to all of these actions. But I can't fit to all of them simultaneously, right? Because this is a probability, and I only have one total mass to allocate. Right? I've got one unit of mass to allocate, so I cannot fit to all of them simultaneously. So what will I do? Well, what I'll do is I look at all the different actions, and one of them attained the highest return, and the others obtained returns that were lower, right? And so what I'll be incentivized to do if I want to increase this is move mass away from the actions with the lowest returns from that state and towards the actions with the highest returns from that state, right? Does this make sense? Does anyone have any questions about that? So if a state appears multiple times, then the different actions that appear off that state, I'm incentivized to fit to whatever actions occur off that state that obtain the highest returns, because I have to trade these off against one another. Okay. Yeah.
Is that if the state appears multiple times in the mini batch?
Yeah, in this data set. So it's if the state appears multiple times in this data set, then when I try to fit this objective, then I have to trade off between the different actions that occur off that state. Yeah, entirely right. Okay. So reinforce high-level summary. Reinforces model-free because you just sample a data set of trajectories from the environment and then you learn directly from those trajectories. You don't need the environment dynamics. You don't need to learn the dynamics. So it's a model-free algorithm. Reinforces on policy. Why is this? It's because the data that reinforce uses for a single update is data sampled using that policy, right? So I have my current policy. I sample data using that policy, and then that data is what I use to perform my update step. So, and then once I've used that data, I discard it. So an off-policy algorithm will use a memory replay buffer, fill it up, and then keep using old data. Whereas an on-policy algorithm won't use a memory replay buffer in general, and will instead take the experience that it gathered, use it for some updates, in this case just a single update, and then throw it away and not use it again. Because as soon as I've changed my policy, that data is now off policy and I can't use it again. So that's so reinforces on policy, and reinforces a pure policy gradient method or vanilla policy gradient. It's sometimes called vanilla policy gradient. It's another term for the same algorithm. So by pure policy gradient, we mean that it learns a policy and it doesn't learn a value function. Right? There's no mention of value functions in anything we've covered. So this makes it a pure policy gradient method. Lastly, you can apply it to any state and action space. So there's no restrictions on the state space, and there's no restrictions on the action space. So I can do this when my probability of action given state is discrete. So there's like 10 actions, and I assign the probability to each one. And I can also do it in a continuous space when my policy is something like a Gaussian, and then I have a continuous action space. So I can apply this to both a discrete and a continuous action space, unlike both DQN and DDPG, where I can only apply it to one of the two. DQN is only for discrete, DDPG is only for continuous. Okay, so where does the reinforce objective come from? So I've given you some intuition for why it works, for why it makes sense as a thing to do. But now we're going to cover where this originally came from. So someone sat down, did some maths, arrived at something, and from that maths, they wrote down the reinforce algorithm. And the maths that it comes from is the policy gradient theorem. This is sort of the theoretical basis of the reinforce algorithm. Okay, so we're going to move on to this now. So the policy gradient theorem takes its starting point. It says, suppose you have a parametric stochastic policy. So I have a policy here, parameterized by some set of parameters theta. And ultimately, the thing I actually want to do, right, the thing I'm actually trying to accomplish is to maximize the expected return under sampling from that policy, right? So at the end of the day, after all my different methods, this is the thing I really care about, right? The task is train a policy that accumulates the highest return possible when you sample from that policy in the environment. All right? So at the end of the day, I want to maximize this thing. So how can I go about doing that? Well, here's an idea. How do we maximize things in ML? We covered this with DDPG. What's our go-to method for maximizing stuff in ML? Maximizing stuff? Gradient ascent, yes. So if I'm doing machine learning, my go-to method for maximizing something is to do gradient ascent, right? So let's just do that, right? Like, why are we messing around with all these value functions? Why do any of that when you could just do gradient ascent, right? So the policy gradient theorem tells us that the gradient of this function, so this is the stochastic policy gradient theorem. We covered in DDPG that there's also a deterministic policy gradient theorem. This is the stochastic policy gradient theorem, and it says that the gradient of this function is just given by this. Right? So the gradient with respect to parameters of the average return, so of this, is just I sum over time steps in my environment, and then I have a grad of the log probability of each action that was taken weighted by my returns. Right? So this is the stochastic policy gradient theorem. So we can go from the policy gradient theorem to reinforce. So let's start with the stochastic policy gradient theorem up top. And we have that this is our expression for the stochastic policy gradient. Okay. And what we're going to do is we'll estimate this gradient by replacing this expectation over trajectories sampled with my current policy by a data set, by an empirical average over a data set of samples of trajectories. All right? So this is just a Monte Carlo estimator in machine learning, right? I'm replacing this expectation with an empirical average of over a data set that I've got. So I gather this data set, and then I replace this expectation by an empirical average over the data set. And that gives me this, right? It tells me that approximately this gradient is going to be given by this expression here, which is just average over data set, sum over time steps in my environment, return, gradient with respect to theta of the log probability of each of the actions taken in the states that were encountered, right? But then if I look at this, right, then this thing here is just the gradient of the reinforce objective, right? So I look at the reinforce objective, which we introduced in the last couple of slides, right? And then if I take the gradient with respect to theta of the reinforce objective, I'm just going to move that gradient inside, end up with the gradient here, and that will give me this expression here, which is an approximation for the gradient of the average return. All right? Let's just pause for a moment. There's quite a lot on this slide. So we'll pause, and if anyone has any questions, now's the time to ask. The log, yeah. So the question was, why does the logarithm suddenly appear? The answer to that is a little bit complicated. It essentially comes down to, so if you think of gradient log probability, right? This is gradient probability over probability, right? And the division by the probability essentially is cancelled out by the fact I'm sampling according to my policy. Right? So this is sort of where it comes from in the end, that the grad log probability is just grad probability over probability, and that over probability is cancelled out by the fact I sample according to my policy. The thing to look up here is, if you look up reinforce, you'll get an explanation as to where the logarithm comes from. But yeah, it's a little bit technical. Other questions? Awesome. Okay, so what we've seen is that doing a gradient step on the reinforce objective, a gradient step of this objective here is equivalent to doing gradient ascent on the average return, right? And we sort of saw a very similar thing in DDPG, which was the last lecture, where I said that the DDPG algorithm was justified by the deterministic policy gradient theorem that says a very similar thing about when you have a deterministic policy, that you can do gradient ascent on the average return by doing sort of gradient ascent on the action values, which is what DDPG does. This is sort of the analogous result for stochastic policies, where what you want to do gradient ascent on now is this weighted log probability. All right. So the next algorithm we're going to cover is reinforce with baseline. So this is sort of a modification of reinforce that's going to motivate the things we do next. So in reinforce, the weights by which we weight each action or each state action pair are the returns, right? And this is the key intuition we should have for how reinforce works. But what we really want is to fit to actions that are better than expected and unfit from actions that are worse than expected. So how do I motivate this? Suppose I'm in an environment where all of the returns are always positive, right? So how can I accomplish this? Any environment where there's no negative rewards, where every reward is positive. If every reward is positive, then every return is positive, right? Or at least non-negative. I never have a negative return. So if all my rewards are strictly positive, then again, I will have strictly positive returns everywhere, right? And this means that all of these weights are positive, right? Every single one of these weights are positive. And so, well, what I'm going to do then is I'm going to try to fit to every single action. But this means that what I'm counting on, the thing I'm relying on, is the fact that if two actions are sampled off the same state, then the one with the higher return is preferentially fitted to, right? But this isn't really exactly what I want. What I'd like instead is that whenever I visit any state, I look at the action I take off that state and I ask, was this action off this state, is this better than expected or worse than expected? And if the action is better than expected, I fit to it. If it's worse than expected, I unfit to it, right? So in reinforce, what you're relying on is competition between the same actions at the same state, or rather the same actions at similar states or similar actions at similar states, right? Because it's a neural network and it will generalize. So you're relying on competitions between similar or the same actions at similar or the same states to drive what you fit to and what you unfit to, right? It's this competition. But we don't really want this. This isn't the best way to go about it. What we want instead is that when an action is unexpectedly good, we fit to that action. When an action is unexpectedly bad, we unfit to that action, right? That's the sort of the better thing to do. And so what we need to do is sort of modify these weights so that instead of encoding absolutely how much return I got, they instead encode, did I get more return than expected, right? Was this action unexpectedly good? Was the return higher than I thought it was going to be, right? And then I'm going to fit to the actions that are unexpectedly good and unfit to the actions that are unexpectedly bad, right? So when I do this, when I fit to whether the actions are better or worse than expected, I get a sort of clearer and less noisy learning signal, because now I'm not relying on competition anymore. I can directly say for each action, should I be fitting to this action or should I be unfitting to this action, rather than instead relying on competition between actions to drive what I fit to and what I unfit to. All right? So the way we're going to go about doing this is introducing a value baseline. So I've already said that what I want to do is say whether an action is better or worse than expected. And so the reinforce with baseline algorithm modifies reinforce so that the weight of each action is no longer the return, but the return minus the value of being in that state, or rather an approximation to the value of being in that state. So I've talked a lot about actions being better or worse than expected, right? And let's remember, what's the expectation of returns? Well, if I condition on a state, the expectation of return conditional on a state is just my state value function, right? And so what this quantifies is, I say, imagine I'm in state st, right? I'm in state st, all right? I have an expectation for how much return I should get off that state. And my expectation is this. This is my expectation for how much return I should get off st. It's my state value function, right? And then I look at the amount of return I actually got when I took a particular action, right? So I take this action and I look at the return and I say, oh, that return was way higher than the return I expected off that state. So this action must be better, must be a good action, right? And then I'm going to get a positive weight here and I'm going to fit to that action, right? Conversely, if my return is lower than the value, then I say, well, I was in state st, I expected this much value, this much return, and I got this much, so that action must have been a poor choice. I must have made a poor choice of action, And so I'm going to unfit from that action. All right? So this is the key idea now, that I'm sort of centering my weights. My weights are no longer, something like all positive or maybe all negative. They're instead relative to how good the state I was in is. Right? If I'm in a really good state and I get a high return, then what matters is whether it was better or worse than the return I expected to get. So you're centering to your expectations here. So these weights now quantify how much return was obtained via this action compared to the return I expected to get when I was in that state. And when an action is better than average, the weights are positive, so GT beats V, and so my weights are positive, and I should fit to that action. When an action is worse than average, the weights are negative, and I will unfit from that action. Yeah?
So is expectation completely based on the average?
Yeah. Yeah. So my expectation, ideally I'd like it to be the average. I don't have access to that, and so instead I'm going to learn this value function and use that as my expectation. So it's not truly centered, it's approximately centered, where the approximate centering is using my value function, which is only an approximation to the actual average. All right? Great. Any questions before we move on? All right, so I think I sort of belabored the point of what the intuition between introducing the value baseline is. So in reinforce, the weights of the returns, what does reinforce with baseline look like? Now the weights are given by the returns minus the state value baseline. So now they look like this. And so now when I weight each action to ask whether I should fit or unfit to it, I will fit preferentially to those actions that are better than expected and unfit to actions that are worse than expected. So I haven't told you yet how I actually get this value baseline. I want the value baseline to approximate the expected return off that state, right? Conditional on that state, what's the expected return? So how are we going to learn this state value baseline? Well, we're going to do the same thing we did when we were trying to learn an action value. We are going to minimize an MSE loss. So it's going to look like this, right? So this should hopefully be familiar from both DQN and DDPG. DQN and DDPG, they learn action value functions. And those action value functions are learned by minimizing an MSE loss against regression targets. And so we now want to learn a state value function. How are we going to learn our state value function? Again, we're just going to minimize an MSE loss against regression targets. How are we going to form our regression targets? So regression targets have to be estimates of state value. So one way you can do this is you can just say, well, my actual state value is the expectation of the return conditional on the state, and so I can just sample that. And this is called a Monte Carlo regression target. So I just ask what were the actual returns obtained off the state, and then I try to fit to these, right? Another way I can do it is using bootstrapped regression targets. So this is how we formed regression targets for DQN and for DDPG. We underwent this process where we started out with the Bellman equation. We then bootstrapped. We then used a 1 minus done signal to zero out terminal state values, and then we sampled. And we can do the same thing here. We can use bootstrapped regression targets. So that looks like this. I've left the 1 minus d out for sort of for succinctness, because otherwise it wouldn't all fit on one line. But the same process that you go through when you're forming regression targets for DQN and DDPG, where you replace this expectation with a sample, and then you replace the next step value with your approximate value function. So these are bootstrap regression targets. And you can use either of these two as value estimates to fit to with your state value function. So this is one of those points where, again, it's less about this is the canonical version of the algorithm and more about what is the general principle behind the algorithm. What matters here is that you're learning a state value baseline, and you can learn that state value baseline by fitting to regression targets, and all they need to do is estimate value. And there's multiple ways of estimating value. So there's multiple ways of forming regression targets. These are both two different ways of forming regression targets, and both of them will work. And they're used differentially in different algorithms for training a state value function like this. Any questions? Great. So yeah, this loss is written as full batch. So in other words, I'm using every single state and regression target that appears in my collection, my data set of rollouts. But I can also minimize this with mini batch gradient descent. So I can subsample 32, say, state regression target pairs and do gradient descent on that particular state regression target pair. Yeah, just do mini batch gradient descent instead of full batch. All right. Okay. So reinforce with baseline. We are again going to have an interaction step, then a policy update step, and then a value function baseline update step. Right. So these steps were in reinforce. Now we're including a value function baseline update. So in the interaction step, I'm going to take my current policy, I'm going to roll it out in the environment and gather a data set of trajectories using that current policy. Then I'm going to perform one update step of my policy parameters by doing ascent on the objective given here, which is just the same as the reinforce objective, except now my weights are given by return minus state value rather than just return. All right? So this is the only real thing that changes about how you learn your policy. You're still doing one step, you're still doing gradient ascent, you're still fitting or unfitting to actions, you just change how you compute the weights. All right? Then I'm going to update my value function baseline. How am I going to do that? For each state, I'm going to compute a regression target, and then I'm going to fit for multiple steps on an MSE loss between my regression targets and my approximate value function, potentially using mini batches. So I'm purposely being slightly vague here about the details, and that's because there are different details you can fill in and have this work. All right? You can sort of choose freely how to compute these regression targets here, and then all that matters is you're fitting your value function to those regression targets. And you can fit for many steps here, and potentially you have a validation set, and you train until you reach a minimum on the validation set. Potentially you just train for some fixed number of steps. You could train until convergence. There's multiple things you could do to decide how to train here. All right. Again, it's a design choice, and it's more about understanding the general principle of how the algorithm works than the exact details. Any questions? Cool. Okay. Okay, so we covered a theoretical justification for the reinforce algorithm. Now we're going to see what's the theoretical justification for introducing the baseline. Where does this come from? So do we need a new theoretical justification? And the answer is, actually, we don't. We don't need a new theoretical justification. The old one works just fine. So the policy gradient theorem tells you that the gradient of the expected return, so my curly j here is just the expected return. This is just the thing I want to maximize. The whole point of RL is just maximizing the expected return. The policy gradient theorem tells you that this expression is true for calculating the gradient of this expected return. But it turns out that this gradient is mathematically equivalent to this expression here. So when I center these returns by introducing a state-dependent baseline for any state-dependent baseline at all, it still gives me the gradient of this. So if I just include in my weights gt minus a state-dependent baseline, it is still the gradient of the same function. So these are two different expressions for the gradient of the same function. Yeah.
Why would this work better then?
Why would this work better? The intuitive answer is because I center my weight, so I'm fitting and unfitting to actions according to expectation. The more complicated answer is, remember that although these expressions are equivalent, I'm going to use these expressions to derive estimators, right? So I start with these expectations, and then I apply Monte Carlo sampling to replace the expectation with an average, an empirical average, over a data set of trajectories, right? So the actual gradients that I'm going to be taking are approximations to this. And it turns out that depending on which one you use, you get better approximations. This approximation is better precisely because of this centering here. So yeah, this is the reason why this expression, the latter with the state-dependent baseline, can be better than the other one. It's because these expressions form the basis of estimators, and those estimators can have a higher or lower variance, and you want the one that's got a lower variance, and in general, empirically speaking, this tends to have a lower variance, and so therefore is a better estimator. All right, does that make sense? Any other questions? Yeah, so essentially by introducing the baseline, we have exactly the same gradient, but we've got a better estimator that has a lower variance. And in practice, usually this baseline we choose is an approximate state value function. So it actually doesn't even matter that our state value function is approximate, because you could use any baseline at all, and it would be good. It just happens that choosing a state value as your baseline is a particularly good choice that happens to work very well in practice. It's not optimal. We don't in general know what the optimal choice is, but this particular choice tends to be very good in practice. All right, questions? Okay. So what we've seen here is that reinforce with baseline actually loses none of the theoretical justification that reinforce has. It just gives us another expression for the same gradient that is easier, gives a more reliable approximation in practice. All right, so now we're going to move on to the highlight of the lecture, Advantage Actor-Critic. Okay. So what we need to do is move from reinforce with baseline to Advantage Actor-Critic. So the reinforced form of the policy gradient, so this is the policy gradient, the gradient of the expected return, and the reinforced form of the policy gradient is this, right? I'm averaging over trajectories, summing over time steps, using the returns as the weights, and then doing grad log probability of action in state. All right, and I'm rolling out according to my current policy. And I've just argued that the reinforce with that there's another form of the policy gradient which changes from using the returns as weights to returns minus state values. And if I've shown you that there are two different equivalent forms for this policy gradient, you might not be shocked to find out that there is in fact a third form of the policy gradient. And this third form of the policy gradient is the Advantage Actor-Critic form, where instead of having the return here, I have the state, the action value of that state. All right, so I replace the return I got from that action in that state with the value of that action in that state. And expect, to see intuitively why this is not shocking, we should remember that this return here, this action value, the value of performing that action in that state, is just the expectation of the return of performing that action in that state. And so all I'm doing here is I'm replacing g of t with its expectation. And it sort of might seem, not completely shocking that if I replace this with its expectation, I can also obtain a valid estimator. So these are three forms of the policy gradient that are sort of go down in terms of how useful they are. So the most useful one is the Advantage Actor-Critic form. Questions?
Can you clarify why it's the most useful?
So the reason it's most useful is because I can sort of take this action value and I can estimate it in like lots of different ways. And this gives me a lot of flexibility about how I can use this form. So this is sort of quite a general form that I'm going to then use to derive a number of different algorithms off. Yeah.
I was just going to say you've lost your supervision.
Yeah. So I'm going to need to learn. What I'm going to reveal to you is I don't actually learn Q a lot of the time. But what I'm going to do is I'm going to take this form and I'm going to use it to derive a number of different ways of estimating this quantity here. Right.
So I guess, yeah, okay. I guess that was my next question, which was that is V based on Q in the same learn system, or do you just learn the advantage as one thing?
Right, so the question was, is V based off Q or vice versa, or do you like learn like the advantage, this whole thing? And the answer is we'll see. Well, we'll go through a few slides, and then it should become clearer how I actually use this form here. Okay, so the advantage actor-critic form of the policy gradient is this, where I've replaced the return now with the action value. And so again, intuitively speaking, what this is saying is, if an action has a higher value than the state value, it must mean that it's a good action and I should fit to it. If an action has a lower value than the state value, it's a bad action, I should unfit to it, right? And what we call this difference of action value minus state value is advantage, and we denote it with an A. And so advantages tell us not how good an action is, but how good is it relative to being in the state. If I'm in a fantastic state and I obtain just a pretty good return, or I take an action that's only pretty good, then I'm doing a bad job, right? I should be, if I'm in a good state, if I'm in a fantastic state, I should be performing fantastic actions, right? And if I'm in a fantastic state and I perform a just absolutely incredible action, then I need to do more of that action, right? So the idea of advantages is, a lot of the time in learning, you don't really care about how good something is in absolute terms. You care about whether it's better than what you could have done, or than sort of the default. And the default here is just the average value or the state value. And so advantages are quantifying how much better is an action relative to just like being in that state in general. So in other words, did I do a good job off this state? So it quantifies how much better an action is compared to the average action taken by the policy in that state. So the state value is just the average of these action values. And so if an action is particularly good, it means it's better than the average action. Okay, so now we move on to how do I estimate this advantage. So I've got this form of the gradient, and I've told you now I'm going to use advantages as my weights. And now the thing to get us a practical algorithm is to give a rule by which we can estimate these advantages. Say how we're going to do that estimation. So the advantage is given by this, and there are many different ways to form advantage estimates depending on how you estimate these quantities. All right? Usually, and so for all of the examples we're going to go through, our state value, we're going to estimate with a parametric neural network that we're going to fit to regression targets with an MSE loss. All right? So this is just the same as the thing we covered before. When I want to learn my state value, I'm just going to fit a neural network to that. So that takes care of the state value. And so the question now is, how am I going to estimate this action value? Because if I know how I'm estimating state value, and I specify a way of approximating action value, I've got a way of forming an advantage estimate, which is the thing I need in the end. So we're going to run through now different ways of estimating action value and what the corresponding advantage estimate is. All right? So first one, Monte Carlo. So I say that my action value is just the expected return off a particular state action pair. And so I can approximate this with just the return off that state action pair, a single sample. Right? This is the Monte Carlo estimate of action value. So I replace the action value, so the average return off a state action pair, with the sample of the return off a state action pair. What's the advantage estimate I end up with? Well, my advantage estimate then will be GT minus V minus my state value function. And what's this? Who recognizes this?
Baseline.
Yeah, this is exactly the same weights as we had for reinforced with baseline, right? So if I use a Monte Carlo estimate of action values, I recover reinforced with baseline. So Advantage Actor-Critic encompasses reinforced with baseline as a special case. All right, reinforced with baseline is just a special case of Advantage Actor-Critic where I use Monte Carlo action value estimates. Another is parametric. So we saw in DQN and DDPG, we covered fitting a parametric action value function. Now, when I fit this, I'm going to need to form regression targets. When I form those regression targets, I might want to bootstrap. If I bootstrap, the Bellman equation I should be using to form those regression targets should be the Bellman equation for my policy pi. All right. So again, we're trying to get comfortable with how do we form regression targets in the general setting? How do we use these Bellman recursions to actually create algorithms? And what I could do is I can parametrically fit this action value function, and then I can use that to form an advantage estimate. So in this case, my advantage estimate is just parametric action value minus parametric state value. All right, that's the advantage estimate I have. The last one we'll cover is bootstrapped. So I say, okay, the value of taking a particular action is the expectation over transitions following that action of the reward I get plus discount factor, the value of being in that next state, right? So this goes way back to the second lecture where we're covering dynamic programming, and we covered that what's the value of an action? Well, the value of an action is in expectation, what's the immediate reward I'm going to get, plus what's the discounted value of the state that I end up in, right? So this is the bootstrapped estimate of or form of action values, but then I can just sample this. So I sample over this expectation to get this, and I bootstrap to replace this, this value function here with my approximate value function, and that gets me these advantage estimates. And this is called the temporal difference error. So you might see this in other places. It's a very common quantity to see in like classical RL, and we call this the temporal difference error. And the advantage that this, no pun intended, the advantage that this form of the advantage estimate has is that I only need to learn a state value function now, right? I don't need to learn an action value function. I only need to learn a state value function, and I can just use it twice to form this advantage estimate. All right? Yeah, so the sort of most basic form of what we usually think of as Advantage Actor-Critic would use this form of advantage estimates. By the way, you can also stick like a 1 minus d in between the gamma and the v to just set state values of terminal states to 0. Again, not here to reduce clutter, but by now we should be beginning to get familiar with like what the general rules are, and you can just always insert a 1 minus d to 0 out the values of terminal states. Great, so this gives us 3 different ways of forming advantage estimates. These are not the only ways. There are many other ways that one could form advantage estimates. One particularly common and effective method is called generalized advantage estimation. So if you're very interested in that, I recommend reading up on that. Okay, so now I think we're basically at the end. Before we cover the final algorithm, does anyone have questions about any of this? Yeah.
For the approach where you use both Q value like estimator and like the value estimator, can't you just use like one model for advantage?
Yeah, so the question was, if you've got a Q and a V, so you're learning both, so in the parametric case, the second case, could you just use one model? And the answer is, yeah, you could. So you could have a model that, if you're in the discrete setting, you could have a model that takes in states and then spits out a value estimate for the state and a value estimate for every action off that state, if you wanted to. And these would be different heads of the same neural network. You could also, if you're in the continuous setting, have some fancy way where you can, again, estimate both the state and the action value off the 2 heads off the same network. So yeah, I've written it as if they're separate networks because they have separate parameters, But yes, you could use the same network and have two different heads for computing action values and state values, respectively. Any other questions? Great, so let's sort of finish up. Advantage Actor-Critic, we're going to have an interaction step, a policy update step, and a value function baseline update step. In the interaction step, we do a collection of rollouts. This generates a trajectory, a data set of trajectories. Then, in the policy update step, we're going to go through every state action pair in our data set. And for each one of those state action pairs, we're going to form an advantage estimate. And this forming of the advantage estimate, I'm being purposefully vague because you can do it in many different ways. We covered 3 of them before. There are other methods one can use for forming advantage estimates. Then, again, I perform a single update of my policy parameters by doing ascent on this objective, where the advantage estimates are now my weights. So again, I'm fitting to actions that have a positive advantage and unfitting to actions that have a negative advantage. The more positive the advantage is, the more I fit to it, and the more negative it is, the more I unfit to it. Then I'm going to fit my value functions using an appropriate method, which is going to usually be a mini batch gradient descent on an MSE loss for many steps with appropriate regression targets. And again, being purposely vague about what I mean by appropriate regression targets, because there are many valid choices, and these different valid choices lead to different versions of the same underlying core algorithm and underlying core framework. And then I just loop this right back to the start. Okay, last slide, high-level summary. So A2C is model-free. It learns directly from experiences sampled in the environment, just like reinforced with baseline. It's on policy. You get your data set of experience, you do one policy update step with it, and then you discard it, right? There's no memory replay buffer, so it's an on-policy method. A2C is an actor-critic method. It's the canonical actor-critic method. It learns a policy and a value function, or potentially 2 value functions, all right? So A2C is actor-critic. You're learning both a policy and a value function, and the role of the value function is forming advantage estimates that are then going to be used to train the policy. And you can apply it to any state and any action space. It can be applied to discrete action spaces and continuous action spaces. Great, thank you all very much.